The effect of hydrogen bonding on properties of ethanol. Now, for ethanol, we also get the hydrogen bond. The boiling point will be affected because ethanol consists of hydroxyl group, the OH group there, as the hydrogen is attaching to the oxygen. So it is the electronegativity oxygen. It will draw the electrons to the oxygen side. As a result of that, hydrogen will be delta positive. The delta positive will be attracted by the oxygen lone pair for the neighboring ethanol molecules. The ethanol molecules are held together mainly by hydrogen bonds with each other. Ethanol has a higher boiling point than compounds with comparable molecular mass. So, how can we show the hydrogen bonds in the ethanol, which is the lone pair attracting to the hydrogen atoms, neighboring hydrogen atoms in another molecules? This hydrogen atom is attaching to the oxygen, which is the highly electronegativity atom. So this is the hydrogen bond. However, the boiling point of water is greater than that for the ethanol because water can form two hydrogen bonds per molecule. So there are two H and then two lone pair. As a result, it can form two hydrogen bonds per molecule. While ethanol can only form one hydrogen bond per molecule because although it has two lone pairs in the oxygen atom, there is only one hydrogen atom per ethanol molecule. As a result of that, it will be one hydrogen bond per molecule in the ethanol. As a result of the less extensive of hydrogen bonding between the molecules, ethanol is as viscous as water because there are some extensive of hydrogen bonding. However, the viscosity should be a little bit lower than water one. While for the solubility in water, ethanol is soluble in water because there is hydroxyl group. The hydroxyl groups enables its molecules to form hydrogen bonds with water molecules. The hydrogen bonds can be formed here with the water. So it can be soluble in water. That is here. A lot of water solvents, it can dissolve into the water. So we say that it is if water can form hydrogen bonds to the solute, then the solute will be soluble in water. So that is here. The hydrogen bond can be formed like this way. Well, if there's water form hydrogen bonds, but the solute cannot form hydrogen bonds with the solvent, that is the water, then the molecules will be hanging around, and then the solute will not be soluble in water. As a result, we say that there will be two layers, so they are not soluble with each other. Ethanol molecules interact strongly with the water molecule, so ethanol and water are completely what we call the term soluble, actually is miscible. They can mix well with each other. Ethanol and water can be miscible. It's completely miscible with water, and ethanol has a high boiling point, and also it has the high viscosity as well. So for the comparison, the strength of van der Waals force and the hydrogen bonding and then the covalent bonding. So here we have to think about the intermolecular forces, which one is stronger. So when we consider about the molecule, whether it is polar or not, we have to think about, oh, if it is not polar, then it has van der Waals force only. But if it is polar, we need to think about whether there is any hydrogen atoms bounded to FON. If yes, then it is hydrogen bond. If no, it is the van der Waals forces, but it is the dipole-dipole interaction. While if it is non-polar, it is just the London dispersion force. But if there is any hydrogen atoms that bonded to FON, then it will be hydrogen bond with the van der Waals forces as well. So both forces exist together. But we can take a look for this one. The intermolecular force, actually, it is varied. For van der Waals force, the strength and the covalent bond strength, you can see it is not comparable. Actually, the covalent bond strength is about the magnitude of 100 to 1000. But for the intermolecular force, it is just 50 or 20 to 40. Now, actually, Van der Waals force has a great variation for the strength. That is starting with the 0.01 kilojoule per mole. That means we need to use 0.01 kilojoule per mole to separate the molecules, or we need to use 50 kilojoule per mole to separate the molecules. So we find that the Van der Waals force actually it can be a great force. But the hydrogen bonding in general, it is on average, it is quite strong. So the relative strength, we say that when we compare, you'd have to base on some same molecular size, because Van der Waals force depends on the molecular size. If it has a very, very great molecular size, then the Van der Waals force will be greater. So when we compare the theaters, we have to get the similar size, in fact. So comparing the strengths of intermolecular forces in different liquids by comparing the evaporation rate. When a liquid evaporates, for example, water, the water molecules at the liquid surface must gain sufficient energy to overcome the intermolecular force that's holding them first. That is, when we want the water molecules to go out, it has to break the intermolecular force. That is the Van der Waals force and the hydrogen bonding. So the liquid must absorb heat, thus causing a temperature drops in the surrounding. So that is, it absorbs heat and then escape the water molecule to the air. The stronger the intermolecular force, the longer time it will take the evaporation as well. So we can use this to compare the intermolecular force strengths as well. The final one is about the solubility rule. We have to remember that as the rule is like dissolve like. That is, if they are similar, for example, if we have nonpolar solids, it can dissolve well in nonpolar solvents. While if we have polar solids, it can dissolve well in polar solvents. So solid-solid, solid-solvent, and the solvent-solvent interaction, if they are in a similar magnitude, that is, they are similar strength, then they can interact with each other, and then the molecule of the solid can go to the solvent, while the solvent can go to the solid as well. So they can mix well, and then we will say it is dissolved, or they are miscible with each other. Just like this one, the ethanol. So when we add some ethanol and water together, I will try to make it faster. Anyway, so this is the ethanol, and then this is the water, distilled water. And then when they mix together, like this one should be done in the form 1,2-IS. So the ethanol and water can mix together. If we add some colored ink into, for example, this one, it is orange in color or yellow in color in actually, and add some blue color, and which is the food color, the blue one, and then yellow. If they can mix well, then it should be having a green color. So when they are mixing, putting together, it will form a green solution, a homogeneous solution that is in one phase. We cannot see two. So when we put back into the measuring cylinder, you can see they mix well. They don't have two layers. In fact, they mix well and then get one layers of that. So in Form 1-IS, one of the points we have to get you recalled is the particles as the solubilities, they have different sizes of the molecules. They can pack more effective. As a result, the volume is smaller here. So this is just the branch that I want to mention here. How about the solute? If the solute has a greater force than the solvent, the solvent has the weak forces between itself, while the solute has the strong interaction with each other. So the solvent cannot go to break the solute. As a result, they cannot be mixing well. While another one, if the solute and solute has the weak interaction, while the solvent and solvent has a great interaction, that means, again, the solute cannot go and break or separate the solvent-solvent interaction. As a result, high solubility of nonpolar solutes in nonpolar solvents, only London forces of van der Waals forces are involved. Solute-solute, solvent-solvent, and solute-solvent interaction are similar in magnitude. So if they are similar in magnitude, they can dissolve well. While the solvent molecules may readily penetrate the crystal structure of the solid. So they can penetrate with each other. It is also easy for solute molecules to penetrate between the solvent molecules as well. So distribute themselves throughout the liquid. As a result of that, the solid dissolves. While the low solubility of nonpolar solutes in a polar solvent. In a polar solvents, dipole-dipole interactions, which is a very, very strong and greater force attraction, cause the solvent-solvent attractions to be greater than either solute-solute or solute-solvent attraction. So the associated solvent structure is not readily to break down, or it is not readily broken down. Dissolving some organic compounds in water, for example, some ionic organic compounds, so it is ionic, then it can dissolve in water. While some compounds with hydrogen bonding, for example, it consists of nitrogen, it can form lone pair, it can form hydrogen bond with the lone pair electrons on N and the hydrogen atoms on water. Then if they can form hydrogen bonding, then the organic compounds can dissolve in water. Or some small non-ionic organic compounds with the polar groups, such as here, the CO double bond. But the O lone pair can dissolve, can form hydrogen bond with water. As a result, it can dissolve into water. So if water can form hydrogen bonds to the solute, then the solute will be soluble. So form hydrogen bonds, soluble. The molecules of water, actually, they are held by strong hydrogen bond. As a result, if here it has no hydrogen bond can be formed to the water, then it is not comparable strength. It cannot form hydrogen bonds to the solute, then the solute will not be soluble. As a result, two layers formed. Just the same case, when ammonia dissolved in water, the two kinds of molecules orient themselves. Negative end is facing to the positive end. Then hydrogen bonds can be formed. So the hydrogen bonds is formed from the N, the lone pair of N to the hydrogen, or the oxygen lone pairs to the hydrogen. So that's the end of this chapter.